Welcome to Operations Research. Today, we are diving into the Northwest Corner Rule. Imagine you are a delivery manager with multiple factories and warehouses. You need a quick, valid shipping plan to get goods moving immediately without worrying about the absolute lowest cost just yet. This rule is your starting point. It is a fundamental algorithm that gives us an initial basic feasible solution, setting the stage for complex optimization later. Let us explore how this simple yet powerful technique works. Before we look at the rule itself, let us understand why it matters. In operations research, the transportation problem is the mathematical challenge of finding the best way to ship goods from multiple sources to multiple destinations. But optimization algorithms cannot start from a blank slate. They need a mathematically valid starting point, which we call an initial basic feasible solution. This is simply a valid plan that ensures every factory ships only what it has and every warehouse receives exactly what it needs. It might not be the cheapest plan, but it gets the math started. Now that we know we need a starting plan, how do we build one quickly? The Northwest Corner Rule is a systematic algorithm designed exactly for this. It gets its name because it strictly begins allocating resources at the top left cell of your transportation grid, which corresponds to the geographic northwest direction. From there, it blindly allocates the maximum possible amount to that cell, adjusts the remaining supply and demand, and moves either right or down. It completely ignores the actual costs of transportation, focusing entirely on speed and simplicity to give us a valid baseline. This intuitive process translates into a very simple mathematical formula. Conceptually, we can never ship more than a factory has, and we never send a warehouse more than it asked for. So the amount we allocate to any given cell is simply the smaller of the two values between the available supply and the required demand. In this formula, Xij represents the number of units we decide to ship from a specific source I to a specific destination j. Si stands for the total available supply at that source, and dj stands for the total required demand at that destination. If supply increases, we can fulfill more demand, and if demand drops, we ship less. Before we move on, let us see this with a concrete example. We are given 3 factories with supplies of 50, 40, and 60 units, and 3 warehouses with demands of 20, 95, and 35 units. Notice that both total supply and total demand equal 150 units, meaning the problem is perfectly balanced. We begin at the very first cell, representing the route from factory 1 to warehouse 1. We apply our formula, comparing the supply of 50 and the demand of 20. The minimum is 20, so we allocate 20 units. Warehouse 1 is now fully satisfied, so we cross out its column. Factory 1 still has 30 units left in its inventory. Continuing with our allocation, since the first column is crossed out, we are forced to move our finger to the right, landing on the route from Factory 1 to Warehouse 2. Factory 1 only has 30 units remaining, while Warehouse 2 demands 95. We take the minimum, allocating all 30 remaining units. Factory 1 is now completely empty, so we cross out the first row. Warehouse 2 still needs 65 more units. Because the first row is crossed out, we move down to Factory 2. Factory 2 has a fresh supply of 40 units. Comparing 40 and 65, we allocate 40 units. Factory 2 is now empty, so we cross out the second row. We are almost done with our initial plan. Moving down again, we arrive at Factory 3 and Warehouse 2. Factory 3 has a large supply of 60 units, and Warehouse 2 only needs 25 more. We allocate 25 units, completely satisfying Warehouse 2, and cross out the second column. Factory 3 has exactly 35 units left. We move right to our final cell. Miraculously, Factory 3 has 35 units and Warehouse 3 demands exactly 35 units. We allocate the final 35 units. Both remaining supply and demand drop to zero simultaneously. This perfect match always happens at the end of a balanced problem. We have successfully found our initial shipping plan. Let us visualize the journey we just took through the matrix. Look at the diagram on screen. You can see our allocations of 20, 30, 40, 25, and 35. Notice how the red dashed arrows connect these allocations, forming a distinct staircase pattern starting from the top left and ending at the bottom right. This staircase shape is the signature footprint of the northwest corner rule. It visually proves that we only ever moved right or down as supplies and demands were exhausted. Every valid solution generated by this rule will trace a similar continuous path through your grid. Now that we have our staircase path, we must check its mathematical health. When we create our initial delivery plan, we must pay attention to how many individual shipping routes we have activated. In a standard transportation matrix, a healthy, non-degenerate starting plan must contain a very specific number of active routes, which we call non-zero allocations. If our plan has too few active routes, we encounter a condition known as basis degeneracy. This is a mathematical roadblock where the solution lacks enough independent data points. If you do not have enough active shipping lanes, the mathematical machinery used to find the cheapest cost later on will freeze and fail to work. To ensure our optimization algorithms will work, we use a simple formula to calculate the exact number of active allocations required. The formula is n equals m plus n minus 1. Here, n represents the target number of non-zero allocations we need in our final plan. The variable m represents the total number of rows in our matrix, which is the number of factories. The variable n represents the total number of columns, which is the number of warehouses. If our rule produces exactly this target number, the solution is normal. If the count is strictly less than this target, the solution is degenerate. Adding more factories or warehouses increases the required number of active routes. Let us apply this check to the basic problem we just solved. We had 3 factories, so m equals 3, and 3 warehouses, so n equals 3. Plugging these numbers into our formula, we get 3 plus 3 minus 1, which equals 5. The formula tells us we need exactly 5 allocations for a healthy solution. Looking back at our steps, we made allocations at 5 distinct cells. Because our actual count of 5 matches the required target count of 5, our solution is non-degenerate. It is perfectly ready for further cost optimization using advanced methods. Now let us look at a slightly different scenario where things do not go as smoothly. Suppose we have a new problem with 3 factories and 4 warehouses. The factory supplies are 30, 50, and 20. The warehouse demands are 30, 40, 20, and 10. Both total supply and demand equal 100 units. We start at the northwest corner just like before. At the top left cell, Factory 1 has a supply of 30 and Warehouse 1 has a demand of exactly 30. We allocate 30 units. But here is where the anomaly occurs. Factory 1 is now completely empty and Warehouse 1 is completely satisfied at the exact same time. If we cross out both the row and the column simultaneously, we will break the staircase chain and lose an allocation, causing degeneracy. To prevent the optimization math from breaking later, the standard rule is to cross out only one of them. Let us cross out the row and leave the column active but with an artificial remaining demand of 0 units. We then move down to the next row in that same column. Factory 2 has 50 units, but Warehouse 1 has an artificial demand of 0. We take the minimum, allocating exactly 0 units to this cell. Mathematically, this 0 acts as a crucial placeholder, counting as a valid allocation that keeps our path connected. You might wonder why anyone would use a shipping strategy that completely ignores the cost of transportation. The primary advantage of the Northwest Corner rule is its sheer speed and simplicity. In computer science and logistics software, Complex optimization algorithms like the simplex method cannot start from a blank slate. They require a mathematically valid starting point to begin their calculations. This rule provides that starting point almost instantly, requiring no sorting, no cost comparisons, and very little computational power. A computer uses this rule to generate a rapid baseline plan in milliseconds, which it then refines into the cheapest possible plan. Let us summarize what we have learned. The northwest corner rule is the most basic method for finding an initial basic feasible solution in a transportation problem. By starting at the top left and allocating the minimum of supply and demand, it creates a valid, staircase-like shipping plan. We also learned that we must check for basis degeneracy using the formula m plus n minus 1. And we can patch degenerate problems using zero allocations. While it rarely produces the most cost-effective solution, its speed makes it an essential first step. You now have a fundamental building block of operations research.